did not understand how the force of gravity worked before Einstein gave us this
Didn't.
general theory.
This is the only theory which can combine Einstein's theory of relativity with the quantum theory.
Welcome to a fascinating exploration of the enigmatic realm of four-dimensional spacetime with the esteemed physicist and science communicator Brian Greene. In this discussion, we'll journey through the fundamental concepts that underpin our understanding of the universe as we dive into the profound implications of space and time as a unified, four-dimensional entity. With Brian Greene as our guide, prepare to embark on a thought-provoking journey into the very fabric of reality, where conventional notions of space and time are redefined and the mysteries of the cosmos are unveiled. This is Reveal the Mystery. If you are curious to learn mysteries of the world, space and beyond, consider subscribing. The fundamental significance of space and time is widely acknowledged in our comprehension of the physical universe. In our common perception, outer space is often envisioned as a vast expanse through which celestial bodies such as planets, stars, and galaxies traverse. Similarly, the concept of time is so ingrained in our experience that we tend to overlook its inherent peculiarity. Our contemporary understanding posits that space and time are intricately interconnected within a four-dimensional framework known as spacetime, a notion elucidated by the theory of quantum mechanics. It is noteworthy that prior to the 17th century, there was no systematic definition for space and time. In 1687, Isaac Newton's publication of his Principia, which some regard as the most influential scientific treatise in history, dramatically reshaped our comprehension of the cosmos. Newton was the first to articulate a clear definition for both space and time. In his pursuit of formulating the laws of motion, he made a remarkable observation, asserting that space is an immutable and unchanging stage that extends throughout the entire universe, serving as the backdrop for all cosmic events. Furthermore, he expounded on the nature of time, postulating that time is universal, flowing in consistent and equal intervals, independent of one's location, whether on Earth, Mars, Venus, or in another galaxy. Newton's concept of time can be likened to a universal cosmic clock, persistently ticking away in the vast expanse of the universe. This foundational framework, with its associated equations, has proven to be remarkably accurate in describing the motions of celestial bodies as well as predicting the trajectories of objects like rocks in terrestrial scenarios. Even in the context of advanced space exploration endeavors, such as NASA's missions to the Moon, Mars, and other planets, these equations remain a cornerstone of our scientific understanding. Newton laid the foundation of classical mechanics by asserting that space is separate from matter and time flows uniformly, irrespective of events occurring in the world. His ideas on space, time, and motion exerted significant influence over the field of physics from the 17th century until the emergence of Einstein's theory of relativity in the 20th century. In 1905, Albert Einstein introduced his theory of special relativity, which demonstrated that space and time are interconnected within a single structure, which he termed spacetime. Einstein was deeply perturbed by Newton's conceptions of space and time, motivating him to pursue a deeper understanding of these fundamental aspects. He believed that space and time must play more intricate and intertwined roles in the universe if they were indeed real. After extensive contemplation, Einstein cracked the code in 1915, revealing the profound roles of space and time in the cosmos. He realized that they serve as the medium for transmitting the force of gravity, marking a revolution in our comprehension of this fundamental force and setting the stage for numerous scientific and technological breakthroughs. In November 1915, Einstein achieved one of the most momentous intellectual breakthroughs in the history of physics when he expanded upon his concepts of gravitation to formulate the general theory of relativity. Departing from Newton's idea of gravity as an instantaneous force acting over distances, Einstein proposed that gravity operates more as a field, distorting space and time around massive objects. Thanks to Einstein's general relativity theory, gravity can be described as the curvature of space-time in the presence of massive bodies. The stronger the gravitational field, the greater the curvature of space-time and the slower time progresses. This phenomenon is referred to as gravitational time dilation. For instance, if you were on top of a skyscraper, time would pass slightly faster for you than for someone on the ground due to this effect, but it's so minuscule that you wouldn't notice it. However, it becomes significant when considering GPS satellites, which must account for these effects to provide accurate positioning. Special relativity reveals that if a clock is placed on a satellite and compared to an identical clock on Earth, the satellite's clock appears to lag. In contrast, general relativity shows that these clocks will tick slightly faster. The combined effects result in the satellite's clocks about 38 microseconds faster each day. While this may seem insignificant, unaccounted for, these relativistic effects could accumulate to a substantial error in GPS positioning, particularly in situations involving high speeds or extreme gravitational fields, such as near a black hole. A black hole is a region within space-time where the gravitational pull is so intense that nothing, not even particles or electromagnetic radiation like light, can escape its grasp. If we consider space as a tangible entity capable of responding to forces and interactions like more familiar objects, then it becomes subject to the laws of the universe, the laws of quantum physics. However, applying quantum physics to the fabric of space presents formidable challenges. To describe the gravitational field of a black hole in terms of physical quantities, such as the curvature of space-time, we encounter issues that diverge, especially at the black hole's center. To address these complexities, we require a theory that extends beyond the realm of general relativity and delves into the domain of quantum mechanics. Such a theory should allow for a more detailed description, even closer to the center of a black hole, and ideally, provide insights into the physics at the heart of a black hole. Yet no theory has yet succeeded in fully explaining the interplay between the dynamics of matter influenced by quantum mechanics of space-time. One of the conceptual challenges in merging quantum mechanics with general relativity arises from the distinct role of time in these two frameworks. In quantum theories, time serves as an independent backdrop through which states evolve, with particles exploring all possible paths simultaneously, resulting in an amalgamation of these paths. Several theories have been proposed in an attempt to elucidate the nature of gravity, with string theory and loop quantum gravity being the most prominent contenders. In our pursuit to comprehend the fundamental laws governing the universe, we often focus on analyzing the properties of a limited number of particles, or, when considering the entire cosmos, model it as a simplified, homogeneous structure. This simplification is necessary due to the intricate nature of the subject matter, which our current level of understanding cannot fully dissect. Our quest for knowledge follows the footsteps of scientific luminaries like Newton, Maxwell, and Einstein, who demonstrated that mathematical calculations can serve as a potent and reliable guide, leading us into uncharted territories that we have not yet been able to explore experimentally. Presently, a comprehensive and consistent quantum theory of gravity remains elusive, and the candidate models face substantial formal and conceptual obstacles. Moreover, a common challenge is the lack of a means to test quantum gravity predictions through experiments. Nevertheless, there is optimism that this situation may change with the availability of future data from cosmological observations and particle physics experiments. We hope you like this video. Don't forget to like and subscribe our channel. Goodbye.